All right, we're ready to begin our next section, 8.6, quotients with radicals. We're getting used to how to work with them, and so now we haven't seen really any division problems. The quotient, remember, is an answer to a division problem. So we'll be dealing with those today and rewriting and simplifying the expressions with these different radical forms of quotients in them. So take a look. Here are some basic definitions we like to use, and then we will show you what we mean with this first example. So, to simplify radicals with the division look, you must make sure you leave no radicals in the denominator. So we're going to show you how you undo and leave no radicals in the denominator. Also, you should find this to be a very similar process to what we did with complex numbers. When we could have no i's in the denominator, we have a very similar process. And then last but not least, what is rational versus irrational? So if I looked at this right now, the 30, which is a numerator, is a rational number. Now it doesn't mean we have to have a whole, because a fraction by itself is rational. But right now, this radical underneath is not a perfect square combination, and it's considered to be irrational. And so by those standards, right now, the denominator is irrational and the numerator is rational. This process that we're going to use up top, you can see, is called rationalize the denominator. So if you see directions that say rationalize the denominator, simplify the division, it means we have to get that radical out of the denominator. So we cannot have a radical in the denominator, otherwise it would be considered to be irrational. And our directions say we want to rationalize the denominator. So think real carefully. I'm going to get rid of a few of those things because we need to work next to it. What could we multiply a radical 10 by just by itself to make it a whole number we could work with, not a radical? Most of you are thinking of the idea, let's multiply by radical 10. Now, if I multiply by radical 10, I'm going to have to do that up top also, so think of the problem as top and bottom. And I think we did this before, but now we're looking at, really, we have a fancy form of 1 sitting there. And that fancy form of 1 is called, or part of the process called, rationalizing the denominator. So we've got a radical 10 there. We want to multiply by radical 10 over radical 10. I'm going to go backwards and get rid of our fancy form of 1, the red one, and I'm going to leave our fancy form, which was the radical 10. And again, I would focus on the denominator first and make sure that we have no radical numbers left in the denominator. So here we go. Radical 10 times radical 10 is radical 100. And most of you know radical 100 is better known as the whole number 10. All right, from there, we're looking at 30 times radical 10. One of those is a whole number, one of those is a radical. You cannot multiply two different types of numbers. So the best we can do is put 30 over root 10. Let me bring this back down a little, it's a little thick. And now if we did and brought that over to this next line, start looking at what you have. When you look at that, you have to say, wait a minute, that's a fraction. And the 30 over 10 is like reducing fractions, and that's exactly how you should be thinking of it. And so right now, we would be left with a final answer of 3 root 10. So that 3 root 10 that we are looking at here is the original fractional look that was irrational, and we've just turned it to be a rational number. Okay, with that, let's try a couple other looks that'll get just a hair more complicated. This one has our variables in as well. Doesn't matter. We're going to follow that same rule that says we want that fancy form of 1. So right now, if you were going to do anything, some people would say, well, why not just simplify this first? Some people would, some people wouldn't. I say if we simplify it, we keep the 20 where it's at. We know the 25 is a perfect square. It comes out as a 5. We know n to the 7th can only come out as, think of it as a group of 6 and it's left over. And so n to the third would be sitting down there. That's okay, but I can't have a radical, and it looks like we still would have one. So we got a couple things we can do from here. Let's clean it up just a bit more. If we went and said, hey, 5 goes into 24 times, we'd leave the n to the cube, or n to the third on the bottom. That would leave us 4 on top, a 5, an n, whoa, not an m, don't change the letters, n to the third, and a radical n. Now, the problem is that radical n. If we want to rationalize the denominator, we can have no radicals down there. So if we multiply both top and bottom by a square root of n, we should be able to eliminate that square root of n in the denominator. Let's try. Let's multiply that first. We're not going to touch the 5n cubed, which has nothing to multiply with, but the square root of n times the square root of n leaves you the square root of n squared, or better known as n. Up on top, we'd have 4 square root n. But if you now look, we have like variables down below. So final answer, we're looking at 4 root n up on top. That's okay to have a radical in the numerator. It just can't have it in the denominator. And n to the third times n is n to the fourth. Final answer, 4 radical n up on top, all over the whole number, 5n to the fourth in the denominator. That's what rationalizing the denominator looks like with some variables involved as well. What if the entire number is a radical? So there's not two parts. Well, remember, the radical rule said you could split it up. So if you like thinking radical 1 over radical 5, you could do that. And then people would simplify, well, say, hey, the square root of 1 is just 1, right? But that still leaves us a radical in the denominator, and that's where the problem lies. So again, what are we going to do? We're going to multiply by that number that would make this a whole number, and that in this case is the square root of itself. So multiply by itself, and you'll always square it. And squaring it in this case gives you a 5 in the denominator. On top, though, we still have a square root of 5, and that's okay. But this is now rational, and our final answer is square root of 5 over 5. Okay, I think we got one more here. Now, what happens if we have an addition, subtraction going on down there? This one gets a little tougher, but I want you to think of it, they're like binomials. So right away, I'm going to lock them in so I don't try to cancel anything incorrectly. A 2 minus 3 root 5 and a 2 plus 3 root 5, not going to happen. Think of it like we did, a binomial. What would be the conjugate? And that's what these are really called. We can't call them complex conjugates. That was imaginary numbers. But to get rid of it, we're multiplying by the conjugate. When I have a plus or minus, that's what you need to use. And since I have a minus here, its conjugate, in order to be eliminated, would have to be a plus. So if we multiply by 2 plus 3 root 5, we should be able to eliminate all radicals in the denominator. We still might have some up top, but that's okay. So, and again, it's a fancy form of 1. So look carefully at, I've got the same thing on the top, same thing on the bottom. That's my fancy form of 1. So if you like it that way, here's the 1. They don't cancel, they're just a 1, and whatever I multiply on top by, I have to multiply on the bottom. So we'll undo that and actually now do the multiplication. Okay, and we're going to stick with the bottom first, and we have to FOIL. It's first. Ready? First times first. 2 times 2 is a 4, and I'm going to put a fraction bar so we don't lose track of where we're at. There's a 4. Then we go to outsides. Now when you multiply in this case, it's whole numbers times whole numbers, radicals times radicals. So 2 times 3 is 6 root 5. And then inside times inside, that would be these two. That's a negative 3 root 5 times 2, so I believe we're going to get a negative 6 root 5. And then last times last, be careful, we're going to have a negative. 3 times 3 is 9, and root 5 times root 5, some people say is root 25. And yes, that's another name for 5, so be careful here. Also be careful here in the middle. We got a plus 6 root 5 and a minus 6 root 5. So a 4 subtract 45 is what we have left. 4 subtract 45. Looks like we're going to have a negative 41 in our denominator. So I'm going to put that down here, leave it, and now go and handle the top and see what happens there. I'm going to change colors just so we don't get confused. And now here we go. First times first. It's going to be similar, so you'll be able to use some of your work. There's the 4. Outsides would be 6 root 5. Insides would be 6 root 5. Notice the difference? We don't have 1 plus 1 minus this time. They're both the same sign. And then last times last would give us a 9 root 25. We did that down here, so 9 times 5, or 45. Let's clean it up. Put the numbers all together. 45 plus the 4 in the beginning would give us 49. And the 6 root 5 plus the 6 root 5 is just taking like terms. If I have 6 of these things and 6 more of these things with like terms, I will have 12 of them total. And what were they? They were root 5. So I will have 12 root 5. So our final answer, and it does not have to be separated because this is not complex numbers, we can leave it as a fraction look. 49 plus 12 root 5 over a negative 41. We use the conjugate, and that's as tough as they're going to get. A lot of them you will just get to multiply using the single radical, but that will be the toughest they get. And the only time you have to do that, the conjugate idea is when you see that plus or minus in the denominator. And you always want to use the opposite sign to get that conjugate. Okay, so a little more practice with these, and we should be experts.